So, if we pick up, let's call this Lecture 12, page 1. We'll say that this is a, I don't know if we're going to work both problems. I've got a couple more examples here. We may just work this one and call it good and say there is additional information there if you need to see one. But here's a heat exchanger problem. Now, if you look in the 580s, 590s, 5100s in the Changle and Bowles text, you'll probably find a problem similar to this. And the problem statement is going to say that a thin-walled, double-pipe, counterflow heat exchanger has a cold water stream that is being warmed by a hot water stream. And we want to know what is the temperature of the hot water coming out. So there's a bunch of adjectives there. When you read one of these problem statements, like I said, it's going to say something like a thin-walled, double-pipe, counterflow heat exchanger. What the, Steve, what is, well, that just means adjective, adjective, adjective. Heat exchanger is really all it means. Thin-walled, so if it says the heat exchanger is thin-walled, that means there's very little metal or some kind of wall, a very thin wall between the two streams. Okay, and so the separation between the hot stream and the cold stream is going to be very thin. When that happens, that means that basically there's not a big temperature difference, so to speak. It's like if the wall is really thin, then the temperature of all of that material is going to be essentially the same. Double pipe just simply means you've got one pipe inside of another one, and counterflow means that the fluid is flowing in opposite directions. If the hot water is flowing left to right, the cold water is flowing right to left, as shown in the diagram. So double wall just means that this pipe is inside the other one, and we're just kind of seeing a cross section of it. Again, the thin wall just means it's a very, very fast transfer of heat between the two systems. But as we mentioned when we first introduced the concept of heat exchangers, it's not uncommon that you'll have a separate hot stream and a separate cold stream. Those two streams don't ever actually mix. It's just one is used to heat the other, or one is used to cool the other, depending on the purpose of the device. So, if we digest the entire problem statement and synthesize it down to just what are we looking for, they want to know, again, the problem statement is going to say, this particular problem statement says something about determine or estimate the temperature of the hot water coming out. What is the temperature of the hot water at the outlet? Okay. Now, what we know is they've given us here now, I'm going to draw my diagram before I write down my givens, because I'm going to change my subscripts here. So I'm going to draw the inside pipe first. Okay, and then there's this, again, it's a double pipe. So there's one pipe inside the other pipe. That's essentially what you have here. So I've got cold water coming in, colder, slightly warmer, but cold water going out. I've got hot water coming in and hot water going out. Now this is what I might suggest. Let's call the inlets 1 and, now let's call the cold water stream 1 and 2. Let's call the hot water stream 3 and 4. Okay, you could call it hot in, cold in. Right, this is my hot stream. This is my cold stream. Okay, so you could say hot in, hot out, cold in, cold out if you like. I'm just going to label them 1, 2, 3, and 4. Now, why would I do that? Well, it's a little easier to write. The C sub P, the specific heat, so some of the things they've given me here. The specific heat for the cold stream, I'm going to label that 1, 2. C sub P for the cold stream. What's this value here? They said is 4.18 kilojoules per kilogram Kelvin. That's basically the specific heat of liquid water at room temperature. Okay. They've given me the temperature of the cold water in, I'm calling that 1, is 15 degrees C. They've told me that the cold water gets heated up to 45 degrees C. T2, again, I'm calling the outlet of the cold 2, so that's 45 degrees C. They've told me the specific heat of the hot stream, the little smaller pipe inside here. C sub P, and I'm calling that 3-4. The hot stream is 3 to 4. They said that this is 4.19 kilojoules per kilogram Kelvin. Your specific heat will increase as temperature increases. Not by much, but a little bit. The hot stream is at a higher temperature, so a higher specific heat content. The hot temperature coming in, that's T3, they said is 100 degrees C. Right? The hot water coming in, T3, 100 degrees C. They want us to find the hot out, T4 coming out. Now they've also given me here in the diagram, notice they've given me a mass flow rate here, so the mass flow rate at 1, right, so this is 1, so the mass flow rate coming in at 1 is 0.6 kilograms per second. And they said the mass flow rate here for the hot water at 100 degrees C, and it's coming in, so m dot 3 is 3 kilograms per second. Something else that was given in the problem statement. Okay, so some assumptions here. We've been told we can assume that it's liquid water at all points. That's a fair assumption because the highest temperature here is 100 degrees C. So if there's any pressure at all, if the pressure is any higher than 1 atmosphere, and it will be for it to flow through here most likely, so as long as the pressure is more than 1 atmosphere throughout the entire system, it's all going to be liquid, okay? Because it's starting at 100 here, and it's going to cool down from here to here, okay? Okay. They just want to know the temperature of the hot water coming in. So when we first introduced heat exchangers, I said you can do one of two things. You can either say, that two approaches with your first law analysis. First approach is you can consider these two separate systems. Separate systems meaning you've got the hot stream is one system. You've got 3 and 4. Mass coming in at 3 and 4. And the hot system is losing heat to the cold system. So the heat is going into the cold system, coming out of the hot system, this being 1 and 2. So I could say Q for the cold system, I could say Q in plus the energy of the mass in minus the energy of the mass out. For the hot system, I could say the energy of the mass in minus the Q out minus the energy of the mass out, and it's the same Q for the two of them. Okay, so that's one approach. I'm going to approach it. This works really good if you need to know the heat transfer between the two pipes. In this case, they did not ask that. Right? They only asked what is the temperature at the outlet. I think we've got everything we need there. Move this to the side. So I think we've got everything we need to just do, I don't think we would need to find, on the screen. Yeah, I don't think we need to find this heat. I think all we need to do is find T4. So state 2 is one large system. Okay? So if I have one large system, and you could redraw this. I'm just going to draw a generic system here and say that I've got E mass in here at 1. Got E mass out at this is 4. Got E mass in. This is E dot mass in coming in at port 3, and E dot mass going out at 2. We say, all right, what other energy is crossing the boundary? Well, if it's a heat exchanger, it's probably not losing or gaining heat from the environment, at least not significant heat from the environment, unless the environment is one of the streams, unless you're pulling air in and kicking air out. In this case, you've got two different streams of water, so they're probably not gaining a whole lot of heat from the outside. You just have mass crossing the boundary. I don't see anything doing work here. There's nothing applying a force. There's no electricity. It's just mass, mass. That's it. So the first law says, again, add the ends, subtract the outs. If you've drawn a diagram, labeled all the energy crossing the boundary, all you've got here is that E dot M1, we'll say, plus E dot M3, E dot for the mass at 1 and 3 are both in, and subtract the outs. That's E dot M2 minus E dot M4. So the subscripts are, think about subscripts as not necessarily set in stone, black and white things. Subscripts are really what you need them to be to make sense. In this case, I'm just putting an M there because I'm being lazy here. I don't want to write mass. There's no reason to write in and out, as I've already defined 1 and 3 as my inlets for my diagram. 2 and 4 are my outlets. So if we assume that it's steady flow, and that might have been given in the original problem statement, but I didn't write it here. So let's just assume steady flow so I don't have a differential equation. Otherwise, I've got dE dt. It's a differential equation, and I'm going to have to do something different with it. Assuming we haven't had differential equations yet, let's just say it's equal to 0, and we move on. So, what about kinetic energies? Well, remember our list, right? So do we need to worry about, because what are the energies? What kind of energies does this mass have? Well, it's got enthalpy. It might have potential energy, and it might have kinetic energy. Well, let's assume the potential energy changes are negligible. So we'll write that out over here as an assumption. So that leaves enthalpy and kinetic energy. So what about the kinetic energy? And I said, well, there's a list. In the last lecture, I said there's a list of like 4 things. Is it a nozzle or a diffuser? No, it's not a nozzle or diffuser. Okay. Did they give me the speeds? I don't remember what order I wrote these in, but are they asking for the speeds? They're not asking for the speeds. Did they give me the speeds? No, they didn't give me any speeds. I don't know the speed at the inlet or the outlet. Do I have enough information to find the speeds? Well, I don't have the areas. If I knew the areas of these inlets and outlets, maybe. But that would be about it. So no, I think we're going to have to assume, and I think it's a fair assumption, the kinetic energy is going to be pretty constant. It's not going to be a significant change. If it does change, it's going to be pretty small compared to the enthalpy change. So each one of these is going to be m dot 1 h1 plus m dot 3 h3 minus m dot 2 h2 minus m dot 4 h4. Okay. And that whole sum is going to be 0. Add the ends, subtract the outs. Now, what do I do here? I've got more than one mass flow rate. I only know these two. I don't know, I wasn't given these two, so what do we do with that? Well, remember conservation of mass is going to tell me, if I just assume that this is one pipe, the mass flow rate at 3 is going to equal the mass flow rate at 4 because I'm assuming steady flow. And the same thing at 1. The mass flow rate at 1 is going to be the same as mass flow rate at 2. These two are going to be equal. And the mass flow rate at 3, which was given, is going to be the same as the mass flow rate at 4. All right, next video.